Starting with sine, I want to take a portion of the function of sine that will pass the horizontal line test so that its inverse will pass the vertical line test. It also tends to be good convention to try to use the values close to x equals 0 as much as possible. So I will try to use the original origin point, and I'm essentially going to trace along sine until I would fail the horizontal line test. If I draw along this curve, so far so good. But once I get up to this point up here, where x is equal to pi over 2, if I were to go any further from here, then what I'm going to have is going to fail the horizontal line test. So I cannot go beyond that point of pi over 2. This portion of the curve would pass the horizontal line test. But I can include more if I go backwards. If I go backwards from 0 down to technically negative pi over 2, I still am going to pass the horizontal line test. But if I go anywhere beyond or below negative pi over 2, then I'm going to fail the horizontal line test, and what I will have as a result will not be a function for an inverse. This is the section that I'm going to be using to graph our inverse sine. So essentially, we're going to flip the x and y coordinates we have for any given point. That means that we will still have 0, 0 right in the middle, but instead of x of pi over 2 and y of 1, we will have x of 1 and y of pi over 2. It's going to put us up here. And instead of x of negative pi over 2 and y of negative 1, we'll have y of negative pi over 2 and x of negative 1. To connect these accordingly, note that the original curve, best way to think about it is that it gets closer to the y-axis and then it goes down to the origin. So it's kind of pushing towards the y-axis first. This is going to do the opposite for the inverse. It's going to go towards the x-axis, come in like this, and then back up. That's what would happen if you flip it over the equation y equals x. Very important note about this. This curve that I have drawn here for the inverse sine function, which can either be written as sine to the -1 of x, or is sometimes also written as arc sine of x. You'll see me more often use that second notation of arc sine of x. This curve for arc sine of x, or the inverse sine, is the entire thing. There is no more to this. It is not a periodic function that's going to repeat any pattern, because if it did, this pattern would start to look something like this, where it starts to go down and starts to curve down again. Basically, instead of oscillating around the positive x-axis, or the x-axis, it'll be oscillating around the y-axis, which is not a function. So, as weird it may be, this is the entire curve. It starts at one point and it ends at one point. It doesn't start somewhere and go infinitely, or go from one infinite value to another infinite value. This is the entire thing. In terms of properties of arcsine, the domain is going to be the same thing as the range of sine of x. The range of sine of x was -1 to 1. Likewise, that is the domain for arcsine. Very important point about that. That means what you're plugging into an inverse function is not an angle measure. For normal trig functions like sine and cosine, yeah, you plug in an angle measure in radians or degrees and you get a ratio back. The inverse does the opposite of that. You plug in a ratio of sides and then you get an angle measure either in degrees or radians back in return, typically radians. It has to be restricted between -1 and 1 because sine still has to be opposite over hypotenuse. If you had a ratio bigger than 1, that would imply the opposite's bigger than the hypotenuse. The range, on the other hand, it is true that the domain was the same thing as the range for sine. However, the range for arcsine is not going to be the same as the domain for sine. Because if it was, then we would not have a true function. We had to restrict and only take a portion of it from sine. That portion, that range, or that domain that we have, that's going to be the new range for arcsine. And that range goes from negative pi halves to pi halves inclusive. You will see me often say that this means that arcsine will give you an angle measure in quadrant 1 or in quadrant 4 of the unit circle. That is technically true because negative pi halves to 0 would be an angle measure in quadrant 4, and 0 to pi halves would be an angle measure in quadrant 1. What's really important about that means is that with the inverse functions, particularly arcsine right now, if I plug in a ratio, I'm not ever going to get an answer from arcsine that will be an angle measure in quadrant 2 or 3. Later on, we're going to really be aware of that and know how to adjust values accordingly if we know the answer should be in one of those two quadrants, because arcsine cannot give an angle measure in those two quadrants. It can only ever give us an angle measure between negative pi halves and pi halves in radian mode. As for the symmetry for arcsine happens to share the same symmetry for sine. That's not going to be true for all functions, but it is here. Both sine and arcsine are both odd functions, and because it's an odd function, that means that if you have a negative input for arcsine, you can also rewrite that as negative arcsine with a positive input. Some see this as a little bit of an easier way to work with and understand what angle measures arcsine can provide. Therefore, instead of thinking about negative pi halves to pi halves, really you just think about angle measures from 0 to pi halves, and then either plus or minus in front of that. For the other information here, this summarizes some stuff about the domain and the ranges, and how these functions interact with each other. If you take sine of an inverse sine function, those are going to cancel out and only give you the input inside of arcsine left over, so long as that value is a valid input for arcsine. Meaning, as long as x is actually a ratio between -1 and 1, then yes, sine of arcsine of x will just cancel each other out. That tends to be less of a concern for us. The bigger concern is actually the second part of this note. Arcsine of sine of x, which is what you're going to do more often than not. If you have a trig function and you want to get rid of it, you're going to apply the inverse trig function to both sides. If you do that, it will cancel each other out, as long as that value of x is between negative pi halves and pi halves. If it is not within that range, then arcsine would not equal that same value. If that is the case, then it is recommended instead to work from the inside out, to evaluate sine of whatever value you're working with, and then take arcsine of that ratio that is output from sine of x. Next, we have inverse cosine. There are going to be some similarities with inverse cosine or arc cosine with arcsine. Starting off with how we come up with it. Again, we want to try to use values as close to x equals 0 as possible. So I'm going to start with this value on the y-axis for cosine. Now I'm going to choose to go in the positive direction. Most individuals prefer to use positive. And again, I'm going to draw until I would fail the horizontal line test. So far, so good. I can keep going through pi halves. But once I get to pi down here at the bottom, if I go any further than that, then I'm going to fail the horizontal line test. That is also true if I were to go any further backwards from where I started. I will fail the horizontal line test. meaning that this is as much as I can really use for inverse cosine of x. So, put that into action. I originally would have an x-coordinate of 0 and a y-coordinate of 1, so now I'll have an x-coordinate of 1 and a y-coordinate of 0. I then would have an x-coordinate of pi halves and a y-coordinate of 0. So I will now have a y-coordinate of pi halves and an x-coordinate of 0. And instead of an x-coordinate of pi and a y-coordinate of -1, I'll have a y-coordinate of pi and an x-coordinate of -1. This is also going to look kind of similar to arc sine that's going to go up and in. It's going to curve up and in like this. Or it curves back up to our final point. Furthermore, just like arc sine, this is the entire curve. It's not going to continue from here. If I did continue to make this pattern, I'm going to fail the vertical line test, and that is no longer a function. So this is it. Which means the domain of arc cosine is the same as the range for cosine itself, which is -1 to 1. That's the same as arc sine as well. So arc sine and arc cosine both have the same domain. They do not, however, have the same range. The range for arc sine was -pi halves to pi halves, or angle measures in quadrant 1 and 4 of the unit circle. For our cosine, our range is from 0 up to pi, which means our cosine will output an angle measure in either quadrant 1 or 2 of the unit circle. Very important to realize that. Furthermore, arc sine had the same symmetry as sine. They were both odd. Cosine, though, is even, but our cosine actually does not have a symmetry. It is neither even nor is it odd, which means that we cannot use any trickery with inputs of negative values. So I can't say if I have a negative input on the function, move that out in front, or eliminate the negative value. Just got to evaluate as it is. Also, like arc sine, we have a couple other pieces of information here. If you take cosine of arc cosine, that will just cancel those functions out to give you x, so long as that value of x was actually a true, valid ratio for a cosine function. So it would have to be between -1 and 1 because cosine is adjacent over hypotenuse. That, just like the previous one, is less of a concern. The bigger concern is the second note here. If you take arc cosine of a cosine function, that will cancel those out and just give you the value of x in return, so long as that value of x is between 0 and pi, aka it is a value that exists in the range of arc cosine. If, for example, that value was 7 pi over 4, 7 pi over 4 is not between 0 and pi, meaning that if you do arc cosine of 7 pi over 4, this will not give you just 7 pi over 4. They are not just going to simply cancel out and give you 7 pi over 4. This is something to be very careful about, and when this happens, it is advised to instead work from the inside out to evaluate cosine of 7 pi fourths first, and then determine what angle measure that ratio would result from. For example, here, our cosine of 7 pi fourths, which is the square root of 2 over 2. This would result in an angle measure between 0 and pi, And the only value where you'd get a positive ratio of root 2 over 2 within that range for cosine is actually just pi over 4. Be very careful about those circumstances. A lot of the examples you will see in this section focus on that concept.